Todd's been a fellow and tutor in physics for LMH since '98. So he's been with the college for over 20 years. And previous to us, he was working for the University of Pittsburgh. So he's here to talk to us about his research today. So without further ado, I shall hand over to Todd, and thank you so much for joining us.
Okay, well, thank you very much, Emma. And I'd like to also extend my thanks to everybody for coming. So this is really fantastic. So what I'm going to do now is I've got a sort of slideshow presentation I'll give you, which hopefully won't last more than about half an hour, maybe less, because I'm kind of hoping that this will be question driven. And then we'll sort of go for a while until people run out of questions, and right, and we'll see how it goes. Okay, so let me see here if I can get the screen shared. All right, so as I said, my name is Todd Huffman, and I do my research at the Large Hadron Collider. So I'm going to talk a little bit about the Large Hadron Collider first, so you have an idea of what it is. It's a huge accelerator that's underneath the ground, so you can't really see it in this aerial photograph. That's why there's a line drawn so that you can see the line. It's 100 meters underground, and what it does, and I said it's huge, it's 8.6 kilometers in diameter. And what it does is we have beams, and you can see the beam line in the inset, which accelerates protons in two directions. So there's actually two beam lines inside this cylinder, and they collide in head-on collisions. And the collisions take place at 4 places. These 4 places are places where the experiments are. There's CMS, ELISE is how they pronounce it, LHCb, and then the experiment that I work on, which is ATLAS. Now, these protons are accelerated to extremely high energies, the highest energies that mankind has ever achieved. And to give you an idea, it's really hard. We measure these things in a unit called an electron volt, okay? 1 electron volt is about the energy that a particle of light has when it enters your eye. So if you look at red light, for example, that has about each photon has about 1 electron volt of energy. This thing has 13 trillion electron volts of energy. So that's 13 multiplied by 10 to the 12, a 1 with 12 zeros behind it. But a better measure that I have of how much energy is how close is it to the speed of light that you can go. You can never surpass the speed of light, but you can get really, really close. And so this thing accelerates the protons to 99.999988% the speed of light, okay, which is fast. All right. So that's what it does. All right. But it collides them, as I said, in one of these 4 places. And one of the places, the ATLAS experiment, this is a picture of the experiment, sort of a schematic view that's opened up. And I guess the main thing I want you to take away from this is how big it is. All right. So these are people, to give you some sort of average size people, as if they were standing around the thing. I've got another picture once where I put a tiger shark in the picture, and the tiger shark just barely covers this middle bit on the inside. So what happens is the protons come in from both ends. That's why it's kind of got these holes in the sides. The protons come in from both sides, and they hit each other in the center. Okay, and this causes the protons to sort of fragment apart. Okay, and when they do, then all of this stuff, this huge detector that's something like 10 meters tall, measures all of these particles that come flying off. And that's where we get pictures from this detector. And the pictures look something like this. Of course, they don't really look like that coming straight out of the detector. I mean, just like your mobile phone or the camera that you're using here, it has to sort of reconstruct an image that then we can interpret. But this is what one of these images looks like, okay? You know, there's all kinds of tracks in the inner part where we track the particles, and then some of them hit more dense areas of the detector and they shower, and that's what all these little showery bits look like, okay, to measure the energy. And the point I wanted to make is that this isn't just, one of the points I want to make is that this isn't just protons running into each other and breaking apart and finding out what's inside the proton. It's more than that. We have this equation, E equals mc squared, which I'm sure most of you have heard something about this equation, okay? Now, the thing that most of you haven't heard is perhaps how profound this truly is. In physics, the most powerful thing in physics is an equal sign, because what it means is that what's on one side is exactly the same as what's on the other side. In reality, not just a mathematical equation, it's in reality. So what this is telling us, what this equation is telling us, is that energy and mass are identical, right? They are no different. So we can turn one of them into the other back and forth. And that's what this detector, or that's what this collider is built for. That's what it's to do. It isn't the protons so much themselves we're interested in. The protons are a convenient package for the energy. They're a convenient way to get a very large amount of energy into a very small volume, and then convert that energy into mass, okay, the M part of the equation. And that mass is not necessarily in the proton to start with, okay? We can create new states of matter that didn't exist before out of basically the energy we've poured into the protons, right? And that's the crucial part of the machine. That's why we built this machine. And that's why we built it with such extremely high energies, is for that purpose, okay? And so that's what I wanted to lead into the research that I do, which I'm going to talk about now, all right? What I've been doing over the last 10 years or so is I've gotten involved in what's called exotics physics, okay? And the whole point of exotic physics, it's a particle physics quest to hunt for things that we don't know exist, right? It's to hunt for things that perhaps some theories predict but haven't been discovered, or maybe even to hunt for things that nobody predicts but that we think we could find if they did exist, okay? So we use this energy matter conversion to find out more about the fundamental particles and their interactions, and that is what my own research is all about, okay? But before I get on to really exotic stuff, I'm going to talk about mundane things, all right? So this is mundane as a particle physicist sees it, all right? So here's the known matter that the LHC makes. These are all the things that we know that we can make there. So we have these 3 generations. You can think of this as kind of like a periodic table of the elements for a particle physicist. And it's fortunate because it's not as big as the periodic table of the elements. So you can just about memorize it, which is also good. Anyway, there's 3 generations, okay? And they have, in the top 2 tiers, we have the quarks. In the bottom 2 tiers, we have the leptons. And these are all the things that we call sort of that make up matter, right? The fermions, the things that make up matter. And then we have this column here on the right-hand side that are the bosons, okay? And these are the force carriers. They're the things that carry the forces between the particles and carry those forces between them, all right? Now, everything that you know in real life, or me for that matter, everything we're used to encountering is actually a very small subset of these, okay? We have the electron and the muon, okay? Now, the muon's a bit exotic. I'll do that one first. It's passing through you at the moment because of cosmic rays, okay? There's cosmic rays raining down on us, and about once per second, one of these muons passes through you. All right. Now the muon, what is the muon? Well, the muon is just a heavy electron. I mean, literally that is all it is. It's got all the same properties as an electron, but it's 200 times more massive than an electron, okay? The electron, you're very familiar with. You're looking at them right now. Everywhere you look, you see electrons, because electrons are on the surface of atoms, which everything is made of. And the other thing that you know, the photon, which I'll get to in a little bit, right, bounces off the electrons and into your eye, so your eye sees them. So you're looking at electrons all over the place. You better be familiar with them, okay? The other 2 that are important, and these are important not because you can see them, but because they hold the electrons in place, and that's the up and down quarks. They're inside atoms, and they're in the nuclei of atoms. So we wouldn't have atoms if it weren't for up and down quarks, okay, and holding the electrons in place. And then, of course, there's the photon, which I mentioned before. Without the photon, you wouldn't be able to see anything. All right. So that's important. And even if you're having trouble seeing things or your eyesight isn't that great, because my eyesight's not fantastic, it doesn't matter. You still know what photons are because you can feel heat. Okay. If you feel the warmth of the sun, those are photons, right? Everything that you feel, in fact, even touching something, you're communicating with whatever you're touching using photons. So they're everywhere. And that's what we're familiar with. Okay. There's one more thing up here that I need to point out, which is important for the whole rest of the talk, because I'm going to talk about it a lot. And that's this guy, this Higgs boson. Oops, better go back there. The Higgs boson down here. I'm going to talk about that a lot because that's the focus of my research. Okay. This was the most recent particle that we made at the LHC. Now we're still making it, of course, but it was discovered at the LHC, at the detector that I work at, in 2012 on July 4th. Okay. Now, exotic searches, right? It's the challenge of the unknown, right? We're hunting for things that are exotic, that are strange. And this covers a wide range of final states and final particles and a vast range of theoretical models, all right? Which, as an experimental physicist, I can assure you nearly all of them are wrong, all right? But that doesn't matter, we look for them anyway. But what we do in exotics is we try to be model independent as much as we can. The key question that usually we ask in exotics physics is, we have this incredible machine, we have this amazing detector, okay? What can we see with that, right? And so there are many of my colleagues who are looking for very, very weird things that nobody predicts actually exist. But if they did exist, we ought to be able to see them with the detector. And that's a sufficient enough reason for many of us to go ahead and look, all right? I'm not quite that exotic, all right? I actually like to do things that have some backing with some of the models, but still, right? This is something that happens. So we look for disagreements, right? We look for disagreements with the models that we have, and in particular with the standard model of particle physics, which is the thing that describes all those particles in that periodic table I showed you, okay? Now, models are really, really important, and even if you don't follow them, okay? And I'm going to illustrate this with a model that somebody had. His name was Christopher Columbus, okay? He had a model, and this was his model that I'm showing you here. He knew that something existed, right? And, it was the spices from the Spice Islands. He knew that they were out there, okay? But, how to get to them, right? And of course, up until now, they had this long overland trek, through the Arab states, and the Italians were making huge amounts of money off of this. And that couldn't be allowed to stand. So Christopher Columbus got a hold of a map from Toscanelli, and this was Toscanelli's map, okay? Now, here's the thing about Christopher Columbus that a lot of people don't realize, okay? He was kook, all right? And Toscanelli, who gave him a map, was also a kook, okay? Because, in fact, the scholars of the day did indeed know approximately how big the Earth really was, right? And they knew how far away the Spice Islands were, sort of, okay? Now, if you know how big the Earth really is, and you know where the Spice Islands approximately are, then you know that this ocean, okay, but you don't know about North America or the American continents, okay, then this ocean becomes about double the size that it appears on this map, all right? So if you are in the 1400s and you know how big your ships are, and you know how much those ships can hold, you know that you will die of thirst, okay? Guaranteed, if you try to cross that ocean to where the Spice Islands must be, right? Everybody knew this, but Toscanelli and Christopher Columbus decided they were going to ignore that, all right? For some reason, they thought the Earth was about half as big as it really was, okay? But he had a model, he had a map, and he took off anyway, okay? Fortunately for him, there was a whole continent in the way, right? Just at about the place where he thought, as you can see from the previous slide, just about the place where he thought the Spice Islands would be, okay? And so he ended up making 4 trips and going back. In some ways, he was really a tragic figure because Columbus never ever figured out that he hadn't reached the Spice Islands. He honestly thought that he'd encountered some, like atoll land masses that, if he could just figure out how to get past them, he'd get to the Spice Islands. He had absolutely no idea. Okay. And that's why the whole continent is called the American continent, not the Columbian continent, because it was Amerigo Vespucci who figured this out and not Columbus. But still, nonetheless, the point is Columbus had a model, okay? And this is just like in most exotic physics searches, okay? It doesn't matter if you have a bad model, right? But you use one anyway. So I thought I'd just show you pictures of everybody in my group that works in exotics physics. So most of these are my students and postdocs that I work with one exception, and that's Cheatham, who has gone on to Berlin, but we still work with her closely. So she takes part with us in the grand tradition of Christopher Columbus. And what I do with some of that group, not all of them, is I'm looking for 2 Higgs bosons, right? One Higgs boson isn't good enough. You got to have 2. So we have 2 Higgs bosons, and we're looking for when the Higgs boson decays into B quarks, okay? The B meson. So each Higgs boson decays into 2 B quarks. So in total, we'd expect to find 4 B quarks. And not everyone in the group does that particular search. These is a subset of people in the group that are working in the di-Higgs to 4B group, okay? So the sort of di-Higgs hunters, all right? So how does this work? Well, as I said, we have the Higgs boson, okay? And on our periodic table, all right, the Higgs boson decays into these B quarks, all right? And this is where it is on that table that I showed you before, okay? Now, there's a couple of numbers I just want to point out. Down here, it says 125,000, okay? You can think of that as a number that's actually let's see, that would be in millions of electron volts, all right? But think of it as a mass, a number that sort of represents its mass, okay? You can see the B quark is quite a bit less massive than that, right? But still, this is the dominant decay we expect the Higgs to decay into. Now, why are we doing this? Why are we hunting for 2 Higgs bosons? All right, I think that's an obvious question, okay? Well, just like the Spice Islands, right? Columbus knew the Spice Islands were there, okay? We know there are something out there. We know there's something out there that is not explained, and it's dark matter is one of the things out there that we know, okay? We can see its gravitational effect on galaxies, all right? This is a picture of the bullet cluster is what it's called. There's a couple of these different clusters that are like this, but this is the most famous one. And what you're looking at in this picture is the red bits, all right? The red and blue bits are not light, okay? I'm gonna make that clear. This is not red light and blue light, okay? The red and the blue are used as proxies, okay? The red bit, actually, well, not quite. The red bit is light, okay? The red bit represents all of the electromagnetic spectrum, and that includes radio waves and light waves, right? And infrared, all of that electromagnetic spectrum that we can collect from normal matter. So normal matter, mostly hydrogen, is colliding and interacting here between these 2 galaxies, okay? The blue has absolutely nothing to do with light whatsoever. The blue is where the gravity is. And we find that out by looking behind this cluster and looking at the galaxies that are behind it and seeing how gravity is distorting those galaxies. And then by knowing how much distortion we see, we can use Einstein's general theory of relativity and figure out how much mass is there, okay? So the blue is showing you where all the mass is, okay? And the red is showing you where all the normal matter is. And it turns out that almost none of the mass is in the red bit. All of the mass are in the 2 blue bits, okay? These are a pair of colliding galaxies. So it's as if the matter and something else came together and the something else doesn't really interact and just kept going, right? Just passed through each other. leaving behind all the stuff that, you know, can collide and interact and you know, sort of thermalize, okay? And this is one of the illustrations. When I saw this, I began to think, yeah, this dark matter is probably some kind of particle, some kind of thing, okay, that has mass that we just haven't been able to see with regular light because it just doesn't interact with any regular light, okay? So there are many searches. We're actually on a quest in all of particle physics. This is one of the quests in many different fields. And so there are many searches, fields searching for this, okay? But they all rely on particles scattering off of each other, okay? So they rely on the dark matter particle passing through the Earth or passing through the detector and then somehow interacting with the detector, okay? But, you know, the dark matter was passing through everything, so maybe it doesn't interact. I mean, what if we've been dealt a bad hand by nature, okay? What if dark matter only has gravity, right? And inertia, which comes along with gravity. It only has mass, okay? And this is why I'm interested in the Higgs boson, or one of the reasons, okay? It's because it turns out the Higgs boson, which is the thing we make at the LHC, it's actually a particle that couples to inertia, right? Anything with inertia, according to our, you know, so far, according to all that we know about the Higgs, and it seems to be true so far, what we think the Higgs does is it actually interacts with things that have inertia. So it would interact with this dark matter, okay, because it would have inertia. So this is one of the reasons I'm looking for Higgs, okay. Now, why do we have a Higgs boson? Okay, what's the reason that we came up with the Higgs boson in the first place in our theories and then went and looked for it? Okay, well, you may have seen the BBC explanation of this. I've really been trying to come up with a better one, but I'm afraid I can't. All right, it kind of looks like this bottom of a wine glass. Okay, you can think of this as that we call it the Higgs potential. Right, these are fancy words for thinking of it exactly like it looks. Thinking of it like a hill. Okay. With you know, that a ball could roll down, all right? It turns out, and this ball in this case is actually our universe, okay? So it turns out that if the universe were to sit right on the top of this potential, okay, the Higgs potential, it gives nothing inertia. At the very center of this sort of potential, nothing has inertia, nothing has mass, okay? It turns out that theoretically, this is very attractive. There's some really cute theoretical tricks you can play where you can predict all the forces of nature as long as nothing has any mass. Theorists love this kind of stuff. They love this stuff, okay? But me as an experimentalist, I point out to them that there's a problem with predicting that everything has no mass, all right? And the problem is that I have mass. So anyway, so the theorists came up with a solution. They said, oh, well, the potential isn't such a way here. You have to slide down the potential. So in other words, at the beginning of the universe, they said when the universe is hot, the potential is like this, okay? It's exactly like this. And there's only one place that you can sit at the bottom, right? And that's right down here at the bottom where, you know, everything has zero mass right at the beginning. But then the universe, of course, is expanding. We know that, right? The universe is all expanding. It's sort of exploding. And as the universe begins to cool, okay, this potential begins to change, right? And it begins to develop these new minima down here, okay? Remember, this is just 2 dimensions. I cut away the, you know, but it's actually supposed to have, you know, 2 dimensions and not just this one, okay? So what happens is that, you know, 13.1 billion years ago at the beginning of the Big Bang, we're sitting in this potential here. And then today, you know, are we down in this spot? And the presence of the Higgs boson is what's telling us that, yes, this looks like what we have, right? That the universe has fallen from this, what they called the false vacuum. It fell into the current lowest state, which is the real vacuum, okay? And one of the things that happens when this occurs, according to the theorists, is everything acquires mass. Everything acquires inertia, okay? Except for the photon. The photon manages to escape, all right? I mean, I could tell you why, but we don't have the time, all right? and it would bore you to tears anyway. However, all we know by discovering the Higgs boson is that this shape looks like what's at the bottom. It looks a little bit curved at the bottom. That's it. All right. Does it really have this shape? Does this potential really go on up and up and up forever? We don't know. Okay. What if the potential actually looks more like this, right? What if the potential goes up for a while and then does one of these cute little squigglies? Okay. It might. All right. If it did, I mean, there's part of me that really thinks this is really interesting, because it would mean that we're still in a false vacuum in the whole universe, and the whole universe might one day tunnel through, because quantum mechanics, this can happen, you tunnel through into another vacuum. All right. So it's only by measuring multiple Higgs bosons that we can tell more about how this potential is shaped. So there's two things. Okay. We can have the standard model, right, where the Higgs gives inertia, and then the Higgs, because the Higgs itself has mass, it couples to itself. So you can get these diagrams where you produce a Higgs and that produces two more Higgs, okay? And the rate at which it couples to itself and also couples to other particles, all right, tells you something about that potential, okay? About whether it will continue going up or whether it will tip over, okay? It also has other things as well. Diagrams like this one, okay, what this thing is running around in the box, all right, is just some particle, okay? Some particle with mass. Well, gosh, you know, that could be all the particles in that box thing, right? Or it could be something that we don't know about, right? Nature knows about everything. Nature has what it has. So this dark matter might be running around this box, okay? And that would help us understand the potential, and it would help us perhaps find it, okay? But in addition, you could just be making that thing directly, right? You could just make this thing, which I'm calling the X, okay? Could be a lot of different things. It could be a standard model Higgs, like I showed previously. It could be something that's called a heavy Higgs, right? You know, how do we know there's only one Higgs boson, okay? Maybe there's a couple of Higgs bosons, and they differ by different masses. I mean, this isn't so crazy. If you remember from way back when I started this whole diatribe, we had the muon, right? The muon is nothing but a heavy electron, okay? So nature has done this kind of thing before, where it replicates the same thing, you know, over and over again. It's just heavier. So maybe we have just a heavy Higgs. And then there's other more exotic, you know, sort of theories. You know, one is called a Kaluza-Klein graviton, okay, where there's many other dimensions, and gravity goes into these dimensions, and the Higgs boson can then couple to this. It's wild stuff, all right? Or it could be just a dark matter particle, okay, that decays into two Higgs bosons, all right? And then, of course, the Higgs bosons decay into the B quarks, which is what we actually see, are these small radius jets of particles that contain the B quarks, okay? As I point out here. Sorry, I got ahead of myself. Okay, so why do we do the B quarks, right? We produce the Higgs boson. Why do we choose the B quarks, okay? Now, this is a hint, right? This is the figure that's been behind me the whole time, all right? And it shows you why we choose two Higgs decaying into 4B. It's because what this pie chart shows is it shows you all the different ways a Higgs boson, a single Higgs boson, can decay, right? And the BB bar, the quark-antiquark pair that are Bs, represent 57% of all the possible decays, okay? The next biggest one is to two W bosons. That's at 21%, right? And then all the rest of them are just little slivers, okay? And so that's why we choose, you know, pairs of B quarks, because, you know, something like if you take two Higgs bosons, about something like 37% of the time, both Higgs bosons are going to give you the B quarks. So that's why we choose that. It's the most common, okay? Now, suppose that we're right, all right? I'm going to be optimistic. When I moved here, they always said you have to be optimistic. You have to be positive in everything you say, okay? Anyway, what happens if there really is a massive particle that decays into two other particles that then also decay? Okay, and then you combine all of that stuff into a mass. All right, I'm going to give you an example, a real example of what happens at the LHC as to how this happens. Okay, this is an example. So this real one, we have a real Higgs boson over here. Okay, this Higgs boson decays into two Z particles, and then each of the Z particles decays into two muons. So we have 4 muons. So we have 4 things. All right, we combine them. We take pairs of the muons, we combine them into the Zs, and then we combine the Zs into the Higgs, and we come up with a number that we think is the invariant mass, the mass of this thing, and we plot that number. Okay, now this plot, okay, is the mass of those 4 things when we stick them together. All right, now you'll notice, so every time that a collision occurs, right, we make this measurement, and a single pip goes into this graph wherever that comes out, and then you build it up. It's called a histogram, and so you just keep building it up. So, you know, after 100 times, or, you know, one event comes in, it might land at 135. You increase this from like 5 to 6, right, and do that, and then another one comes in at a different mass, and you increase that one by a little bit because a new event came in. Okay. If there isn't a particle at a certain mass, then it just sort of randomly distributes, okay? But if it turns out that you really do have something that really has one mass, okay, then every single time you get the 4 muons from that thing, they will always land here at 125 because that's the mass of the Higgs. Every single event that has a Higgs that did this will always end up here. Whereas if you had an event that didn't have that, it could be anywhere, okay? And so if you do this enough over and over and over again, you're going to get more and more and more of these pips are going to show up in the same place, okay? And so as you build this up, this hill, it grows, this peak grows with time and with the amount of data that you collect. And so this is why particle physics are always screaming, we need more data, we need more data, okay? This is how we pull these signals out of this background, right? And this is one that actually occurred, okay? Now, this is analogous, exactly analogous to what I'm trying to do with the 4 B quarks, right? I'm looking for 4 jets of particles with B quarks in them. We take the 4 jets, we combine them in 2 of them into a Higgs and 2 of the others into another Higgs. And then we combine the 2 Higgses into whatever this X thing is, all right? And what we try to do then is plot, just like in this plot, we then plot that 4B mass, or sometimes I list it as the di-Higgs mass, okay? And we see if there's any of these peaks, all right? Now, this is brand new, hot off the presses. It's actually illegal. I'm not supposed to show this to you, okay? So, all right, I can get in a lot of trouble if you publish this, okay? So here it is. Ta-da! Okay, and sadly, there isn't anything there. Okay. Exotics physics is an exercise in disappointment most of the time. All right. So what have we got here? Well, we combine the pairs of jets. We find the mass of the thing that makes the 4 jets. Okay. These are the 4 B jets. And notice all the background. All right. The yellow bit is the background. Okay. So we spend a lot of effort. The game in many of these things is spending a lot of effort trying to make sure we understand the background. You know, does the background match with the data, which are the little dots, okay? Or is the background different than the data, okay? And that's where a lot of our effort goes, all right? Now, if we had seen something, there's a few things on this plot to show you what it would look like if we had seen something. Okay, and that's what like this little green hump here is, okay? This is what things would look like if you had a huge number of a 600 GeV extra particle, okay? They call it a scalar here. Don't worry about that. It's just words, right? It means another particle that had a mass of 600 GeV. It would put a peak right there where the green thing is, okay? There's also a blue one at 400 that's shown here, and a red one at 280. Also notice that this is just the number of events, but notice it's on a log scale, right? So this is 10, 100, 1,000, 10,000. Okay, so it's pretty clear there's nothing. And then this next plot down here below, this is just taking the background, okay, and subtracting the data from the background. Basically, subtract off the background and then look at where do the data sit just relative to the background, okay? So if this green thing really existed, not only would you see these points rise up above the yellow, but down here in this plot, you'd see that all the points were above the red line, okay? And if you look at that, I mean, the eye is incredibly good at statistical analysis, actually, I've found. If you look at that with your eye and don't squint too hard, you will never believe that there's something there, right? It looks like random distributions above and below the curve. So sadly, it doesn't look like, in this run at least, that we found this X particle, okay? But we're still working on the last part, understanding the uncertainties in this and understanding the background, which is why I'm not allowed to show this to you, all right? But we go further than that, okay? What we do is we take a plot like that, all right? And that plot by itself, although disappointing we didn't see anything, it still has information. It has critical information in it. What it has is it tells us that any particle that does exist in that range of masses, okay, cannot be produced at too high a level, otherwise we'd have seen it, right? And so consequently, one of the things we try and publish are limits, okay, to show the theorists that if your theory predicts that you're producing a huge numbers of these things, well, it has to do it within the limits of what our experiments have seen, right? And so that's what this plot is. It's basically just this thing here is the X that we're trying to find, okay? And what this axis represents is something called a cross section, which basically is just the probability of making it, okay? So we measured that if this thing is out there, it has to be with a probability that's lower than this curve, because if it were higher than this curve, we would have seen it. And so we've excluded everything that's above the arrows, okay? And this may not be of extreme interest to you guys or to most people, but it is very much of interest to us and to theorists who are trying to figure out whether that thing wiggles or not, right? Because the amount of wiggles that they put in has an effect on how often we'd produce these things, okay? And so I'm going to wrap it up and turn it over to questions here. So I'm just going to say that, like Columbus, we have models, okay? And even though Columbus had a bad model, he'd still discovered great things, right? And science is riddled with similar stories, okay? So this is Columbus's model, right? With it, he was able to find America for the Europeans. So hopefully we will also be able to find something one day. Let's see. I'm not sharing anymore, am I?
No, that's gone. Thank you so much, Todd. That was such an interesting insight. So yeah, as Todd said, I think we'll open the floor to questions. If anyone has any, feel free to raise your hand or use the chat function. As we wait for hopefully some questions to come in, I don't know, this is a silly question, Todd, so apologies in advance if I'm embarrassing myself, but so the Higgs boson was discovered in 2012.
Yes.
And the point of exotic physics is that you're looking for something that you don't know exists. So how long were people looking for the Higgs boson? Is that quantifiable, or is it just something that?
Oh yeah. No, the Higgs boson was a very big quest in particle physics, because Peter Higgs, who's at Edinburgh, I believe, he was the person who first came up. He was a theorist who first came up with the idea that if there is this sort of false vacuum, it implied there must be a boson that mediates this process of giving everything inertia, and that's why it bears his name. And he predicted this in 1963 or 1964, okay? And really, pretty much once, I would say, it kind of languished in a bit of a backwater until the sort of late 60s, early 70s, at which point Weinberg, Salam, and Glashow came up with a theory that predicted that the Higgs would also give mass to these W and Z bosons. And they were able to give a somewhat of a prediction of the W and Z bosons. And when we built an accelerator in the early 80s, they were found, right? And so the moment the W and Z bosons were found, then the race was on, right? Because in order to have W and Z bosons with mass, it implied that there had to be a Higgs in order to give them that mass, okay? And so the accelerators just kept getting more mass, more larger and more powerful. And it took until we got to the LHC, right? There were like 3 or 4 accelerators that were constructed before the LHC and before it was found, right? And even at the LHC, it took a while. So.
Thank you. That's interesting to know. I can see a question's come in on the chat from Jane. Todd, you said the Higgs boson has inertia. How is inertia different from mass in this context?
Well, yeah, that's a very good question. Inertia and mass, I guess it depends on how you want to define it. The way I define inertia as equal to mass, okay? However, there is something called gravity, and gravity is also coupled to mass, okay? But in actual fact, gravity is like an electric charge. Gravity, we think of it as the amount that gravity attracts something is kind of like its charge, okay? And its gravitational charge, right, doesn't have to be equal to its inertia. It's not true for anything else. I mean, you know, whether something is attracted electrically or not has nothing to do with how much it weighs, okay? But this seems to be true for gravity, though. Gravity and inertia seem to be equal numbers. The amount of gravity, the amount that gravity will pull a given mass is exactly related to the inertia the mass has, okay? So this is, you know, this is how I look at it. So I look at weight as the amount of gravitational charge that you have. And I look at inertia as the amount that you have to push on the brake to stop at a traffic light, okay? Those two things turn out to be equal, but they didn't have to be, right? And that is an active area of research is, you know, is inertia actually equal to gravitational mass? I hope that helped.
Thank you. Yeah, I can see Jane nodding along there. Thank you.
Okay.
A question from Darnesh. The Higgs boson is associated with the Higgs field. Is the Higgs field analogous to the ether that people in the past thought of as what was the medium for light?
No, it wouldn't be actually, because the ether was, well, yeah, the ether didn't impede light, all right, and it was the thing that light would wave, right? So, you know, this is back in Victorian times, and it's not an unreasonable assumption actually. You know, when Maxwell came up with his equations for light, they are equations that are wave equations, okay, just like waves in a pond, right, or waves on a rubber sheet, and you know, the natural thing to think is that, well, excuse me, in order to get a wave, you have to have something that is the medium in which you're setting the waves up, right? You have to have water for the pond, you know, you have to have the rubber for the rubber sheet, or if you're going to put waves on a rope, or even sound waves, right? Which is something Victorians knew well. Sound waves require air, okay? So light, if light's a wave, there must be something that it's waving, that's doing the waving, right? And that was where they came up with this idea of the ether, okay? But what that meant was that as the Earth moved through this ether, okay, it would affect how light traveled. And this was the strange thing that helped tip off Einstein, actually, was he discovered that wasn't the case, right? The Earth, you know, there was no ether that the Earth moved through. All right, the thing that light waves is essentially the electric force and the magnetic force. It's the interplay between the two that allow light to continue to wave in some sense. And that's very specific, all right? But that's why I say it's not the same as the Higgs boson, okay? Or the ether from the Higgs boson, because they're very different concepts, okay? The Higgs field, in that sense, though, the Higgs field is like the ether in that it gives a property to everything that's inside it. It's what gives us the inertia, right? It's the presence of this Higgs field. And it kind of acts as a resistance to an attempt to accelerate something, okay? With one exception, strangely enough, and that's the photon. Since the photon has no mass, it has no inertia, it is not affected by the Higgs field, at least not directly.
Thank you, Todd. Just a couple more questions are coming through, which we've just got time for, which is great. From Robert, is it too early to be thinking about applications for the outcomes of this particle quest, in brackets, aside from knowledge for knowledge's sake?
Yeah, it's, I would say at this stage is very much knowledge for knowledge's sake. You know, and the analogy I always point to, or like to point to, is when Benjamin Franklin discovered that electron, or that particles had two types of electric charge, right? It was Franklin who discovered there were two different types of electric charge, and this was in the 1700s, okay? And, you know, it took about 100 years, but we did tax it in the end. So, you know, it's too early to tell, okay? And it's hard to predict ahead of time which scientific discoveries are going to be ones you can capitalize on and which ones aren't, right? Very difficult. I mean, the fact that, for example, another classic example is the fact that a proton has spin, okay? Proton has this funny property called spin. It can either point up or it can point down. You know, it contributes to the, you know, sort of magnetic field of the nucleus, but usually the magnetic field of the nucleus doesn't make any difference to anybody, okay? But that's crucial to the MRI, right? The MRI machine actually uses that spin property in order to look into the soft tissues of human bodies today, okay? When it was discovered back in the 1930s, you know, who could possibly have thought it'd make any difference? And I think it's the same with some of these particles or some of these things, right? It's hard to tell ahead of time which discoveries are going to be, you know, just interesting things, and which discoveries are going to be crucial to civilization in 100 years' time. All right.
Thanks, Todd. And the last question, I hope that answers you, Robert. Last question from Sarah. The standard model has force carriers for fermions and bosons. Is there a corresponding set of carriers for the Higgs?
Yeah, fermions and bosons. Okay, the Higgs boson is itself a boson. It has spin 0. Okay, and so, you know, it is in some sense a force carrier. It is the thing that is a consequence of this Higgs field, right? This this potential that I showed earlier. Hang on a second. I'll go ahead and share that. Right. This potential that I showed earlier, okay, it is the Higgs boson that creates this potential and that transmits its effects to all other particles. So in that sense, it too is a force carrier. Okay, it's just a very strange sort of force field. Okay.
Thanks. Thanks to everyone for their questions. Looking at the time, we're just about spot on. So unless anyone has any final comments, I think this is a great place to wrap it up. And really, I'd just like to thank you all for joining us on your lunchtime, and thank you so much for Todd for sharing this. It's been really quite eye-opening, and I think the comments coming through there are summing it up. So thank you so much, Todd. I hope you've enjoyed sharing that with us.
Well, thank you very much. I always love the opportunity to talk about my research and hope that it helps.